Thank you, everybody, for coming. Statistician to save the day, huh? You're here for AI, but here I am to bore you. I was supposed to be last to bore you with math and stats and stuff, but hey, I'm going to do it now. I'm Jelena Bradic. I sit in math department and HDSI. I am a statistician, and I was here from day one. So I'm happy that you're here and you want to interact with us. Thank you. So, as I mentioned, this was supposed to be last talk with lots of maths in it, so don't run away. I want to introduce some of my own work to you to show you specifically what are the benefits of causal learning. But let's get started. So we heard that correlation is not causation, and this term has been thrown out a lot, right? But I want you to understand the challenges. It's fine, don't worry. I want you to understand the challenges that machine learning is facing in this world. So when we talk about correlation, what I want you to envision is that correlation only measures, and let's pause, linear relationship between two variables or multiple variables. It does not measure nonlinear relationships. No matter how powerful something is, it just measures the linear effect of one thing onto another. And of course, we know that machine learning is very powerful at predicting such relationships given a bunch of variables that you throw out in it, right? Or inputs, as is the new world in ML. So when I say covariates, this is a very old statistical term. What I mean is features. What I also mean is input space. And in causal terms, these are called confounders. So all of these mean the same thing. They're not and then, they're or. Okay? So very good. So in causation, what we want to actually understand is a change that one variable influences or directly results in a change in the other variable. So I'll give you examples, but the most recent one is that we all lived through COVID. So what is the effect of masking on our health? Or what is the effect of a specific drug onto our health? Or what is the effect of a specific marketing strategy onto the profit of a company? Same question, same math, different question, same maths, and same causal problem. Okay? So what happens here with machine learning is that it's not quite able to capture causation in vanilla form. And my goal today is to show you how I was able, or my group, to improve on that, right? So how can we do something more with machine learning? So as I mentioned, the strength of machine learning is in capturing these intricate correlations that happen in our data. What are the limitations? Cannot distinguish between correlation and causation. For example, I'll give you an example that comes from, say, genetic studies. So I want to study which specific location in a gene affects a disease, okay? And if I plug in a lasso method, which now is called machine learning, but 20 years ago it was called statistics. Anyways, what it's supposed to do is it's designed to predict well, much like deep neural networks, right? And the way it does good prediction is to reduce the number of variables that it's actually focusing on, right? So what lasso does, it's going to give you out of, I don't know, 40,000 SNPs in your gene, it's going to give you 100 locations. And it's going to give you the best prediction because we only have 100 people to look at. So whenever you have limited sample size, another point of today is that you should not be running deep neural networks. Okay, they do not work with limited sample sizes. So how is this related to causation? Well, among these 100 genes, maybe locations is one that's actually causally related to the disease. The one that I was looking at was Down syndrome in particular. But in fact, it's not, because lasso and machine learning is designed to, or there are no guarantees, I should say, mathematically or statistically, that it's there. Maybe it's there, maybe it's not there. So for prediction, I might gather information from other locations that are gathering predictive power around the thing that I care about, but I'm missing the thing that I care about. And I want to highlight that from a mathematical statistical perspective, this is all about hypothesis testing and confidence intervals and p-values, unfortunately or fortunately. So whenever we think about scientific discovery, or I hope somebody is here from industry, so you care about profits of a company. Well, that's hypothesis testing. So any kind of decision making, that's hypothesis testing and confidence intervals. I have to stand for my statistics here. So anyways, so there's some limitations here, right? As I mentioned, prediction gathers power around the thing. So can we leverage that in some way? Well, that's the thing. Can I combine this beauty of very powerful predictive methods, many of them, with some clever statistical nuanced approaches, right? And that's what I want to show you in a few slides. So this is a dense slide, mostly because there was a funny, if you're on Twitter, or X, discussion between OpenAI and a bunch of other ML people. I don't know if you followed a few days ago. So this is a ChatGPT transformer. So very fancy looking deep neural network. And there was a thing mentioned that, oh, there's no curse of dimensionality. Well, there is curse of dimensionality, it's just not because it's in the variables, not in the output space. So particularly, I just assume everybody knows neural networks in this room, so that's probably true. What happens if you want to use machine learning just for causation is that what you're getting out of your predictive neural network is a wrong output. You're getting an output in the space of what I'll call domain, which is Y, or output space, but not the input space. If you care about the questions of why is something happening, or who should be treated, or where should I do the interventions to gather bigger profits, your questions are about X, about confounders, about which gene, which marketing strategy should I change, what intervention should I do, okay? So there is an inherent problem with just grab something off the shelf and apply it, okay? There is a bunch of things I also highlight here. What is different? So for example, how do you see that mathematically? For some of you who are maybe more inclined to think quantitatively, when we use deep neural networks, we think about predictive power. So this is exhibited through accuracy or ROC curves or mean squared errors, right? However, when we talk about causality or effects of something, we actually, as I mentioned, have to think in completely different terms, which are p-values, confidence intervals, effect sizes. And I want to show you, there will be math, I promise, on the slides. How is that seen? Like, what results do you want to see in a paper that convinces you that you have an effect, that your algorithm is actually discovering something important? And I think you've heard a lot about all these different examples of prediction versus causation, so I'll probably skip the rest. So you heard from B-Way, which works on estimating causal relationships between different variables. So she belongs in the causal graphical model world. And you heard from David that there's this other branch called potential outcomes. And we're friends in the sense that you can use this approach or that approach to achieve different things. So where B-Way is estimating errors in the graph, I believe I know them or I can model them. And I only want to estimate effects of such graph on something that I care about. So that's a very different, mathematically very different question, statistically, data sciencey, very different question. However, I want to introduce kind of through pictures, what are these potential outcomes? What are they doing before of this? So here we talked about treatment group and control group. It's the simplest case we can think about, or you can think about A/B testing for a company, A and B, therefore treatment and control. So this is the thing that you see here. Forget about this group of people here. Here we have black individuals that we get to observe. And we have, so these are black individuals are maybe group A, and the white individuals are group B, okay? So we see heterogeneously from each group. Make sense? But if I want to study an effect of a drug, so think about black individuals here, or filled in little pictures, are people who got the treatment. So maybe we give them a COVID vaccine, right? Or maybe we give them something else. We've given them something else. But the other group is the control group. Okay, so the white is the control group. However, what happens is that I want to highlight to everybody in the audience, if you apply machine learning methods or any kind of predictive method just on this group, you will have what we call in statistics biases. So what does that mean? Practically is that algorithm converges to the mathematically incorrect thing that you want to find. So whatever results you get out of it will be wrong, right? And this will have effect on the health or on the profit of your company. So hopefully you care about that, right? Okay, so why is that? Why are there inherent biases here? And I want to highlight that no matter how much of your data you observe, you will have 50% missing data in this setup. So how can you visualize that? So let's pick on this individual here that here didn't get the treatment. For this individual, if I want to study the effect of a drug, I really want to know, had I given the drug to this individual, will they be doing better? But I didn't get to see that because they didn't get the drug, right? So for each individual here, I have their opposites, if you wish, in the control or treatment group that I never get to see, no matter what the data I have. So oftentimes you'll hear this, oh, if I only have enough of data, I can do any questions. It's fundamentally, statistically, mathematically wrong. Well, it depends on the question, right? But if you want to study the effects of something, they're wrong. So, excuse me. So what happens here, or I want to illustrate maybe at a high level, majority of potential outcome methods, what they do is still bear in mind that I don't get to see this mirror of the individual with the treatment, but I would like to estimate it, or I would like to predict it. Okay? And if I want to study the effect, I really should be comparing the output of this individual with the output of the same individual under the different circumstance. So what I want to do, and this is where we can leverage machine learning, is to precisely predict how would this individual behave health-wise, or how would this marketing strategy behave had I done something else. So hopefully you get to see that this line here is my prediction line where I can use ideally any kind of very good machine learning method. How is that actually done? I clearly cannot plug in one observation. Hopefully, one sample size into the neural net doesn't do anything. So what I do is I gather people that I get to observe that are in the opposite group that are somehow similar to this individual. And this word gather is, again, a bit high level, but really you can use any machine learning tool. You can use k-nearest neighbors, you can use a random forest, you can do whatever you'd like, whatever your fancy thing for that you value. And then you want to again, the most predictive or the simplest predictive method is to just average these individuals, right? Average their outcomes, health outcomes, or profit that you get to predict the health outcome of this individual. Again, whether you want to do average or something else, again, this is now your creativity, right? But majority of potential outcome methods, and there are many, the matching, the balancing, the instrumental variables, all of them, are based off of this idea. So you want to gather people that are in the opposite group, but yet somehow similar to what you're studying, and then predict the behavior into the counterfactual. So these are all of the counterfactuals that you have to estimate. And again, it's always 50% missing data. But let me move on to my own work. Somebody should measure time because I have no idea. Yeah, but maybe you can keep me honest. Yeah, okay. All right, so what happens in real life is that I would like to study the effect of a drug over time. So if we study the effect of COVID, it should be studied over time, right? Or if you go to your favorite health professional, you will revisit them during the course of your disease, and you want to make sure that the treatment you're getting is actually making you feel better, right? You're healthier at the end. This is the causal graph that my model would like to assume. It doesn't look as nice and as picturesque as B-Ways, but she was estimating these graphs, and I would just like to use them, and I allow them in my modeling. So I assume that there are these errors here, and really let me show you what it means. So baseline are your baseline covariates. So say age, health, gender, all the demographics that are relevant but not really important typically for health studies. Then based off of those, your doctor will assign a treatment at time 1. this treatment will necessarily both affect your outcome, your health outcome, but it will also affect your, say, genetic information or some other covariates I want to measure about me in the next time point. Does this make sense? So if I take some medication that adversely affects blood sugar or blood pressure, that will be captured in this covariates at time 2. And this error here demonstrates the causal relationship that I assume that the treatment will causally change the covariates. I don't know how, therefore predictive machine learning methods, but I assume that that's there. What happens, and you know, you can carry in this manner forever, right? So the second treatment, which is 3 months apart, 6 months apart, think about cancer. This is a very typical situation in such studies. And I want to study the effect of, say, immunology treatment onto cancer status. Yeah, is it good, is it bad? Okay. Well, very great. What is here, maybe the most important part of this slide is that if you were, most of you know what is regression. You take this outcome and you regress it on everything here that you have observed, right? You plug it into a huge feature vector, you plug it into your, say, maybe regression method or neural network method. However, here, any regression approach, and I should say the neural network is a regression approach at the end of the day, it's just really large model, will not identify a causal parameter of interest, which is whether this drug is effective. What is the size of its effect? Positive or negative? Are we hurting people? Are we curing people? So does not identify means not that there is a bias, it's just completely off. So it's really dangerous. This is not true. If I had one time point, you can run a regression method, you'll have a bias, sometimes big, sometimes small. But whenever you have dynamics incorporated or your problem is as such, what we know is that the causal parameter is not identifiable with regression methods. So you're forced to use, or not forced, but hopefully you enjoy it, you have to use causal method. So I want to highlight some work in this area. It's a huge area of interest. I think the leading, I think David mentioned some people, but the leading researcher is Jamie Robbins in biostat at Harvard. However, even him and his group have not been able to do something that's called sequential double robustness. So that is another maybe point of today's talk, is that robustness is often equal or equivalent to causality. So depends what kind of robustness and all these issues. But double robustness and sequential double robustness was a targeted goal, and it was not achieved. And I'm talking about, this area is not new. It's existed for over 50 years. It's just really difficult problem. We were able, though, to answer this question. How much time do I have? I want to show you some math, so I promise some math. Here, or maybe here, maybe here. So what we've done basically is we designed new loss functions and structured estimation approach that is able to mitigate a lot of these issues about identifiability through robustness, okay? So there's a lot of notation here, but Y for me is outcome. You see it over here. X for me are covariates, or here, sorry, it's S. S1 is covariate at time 1, S2 is covariate at time 2. But I want to highlight, for example, this is a procedure. So there is 4 new loss functions, none of which really looks like least squares or logistic regression. So there's a bunch of classification problems going around in this model. However, what we found out is that logistic regression is not a good loss function to use. And we designed a new one, which looks like a linear term here plus an exponential weight or exponential factor. And this is first time point. Second time point, you'll see the same loss function, but it's reweighted. There's a lot of kind of math drilled into it. Why this is necessary, I don't have time to explain. I'm happy to chat behind or when we have discussions. And you'll see that these other 2 methods here are fancy version of something called imputed least squares, robustly, and weighted least squares. So nothing too fancy, yet the loss functions achieve causality and identify the right parameter. So I just want to show you what type of results in you don't typically see in machine learning is that whatever I'm estimating minus the truth should converge to some distribution. Does not have to be normal distribution, but if I have a distributional guarantee that increases with sample size, whose variance decrease with sample size, I can build confidence intervals, I can build a hypothesis test, I can tell you not only whether there is an effect, but I can tell you how big is that effect and with what certainty, so 95% certainty and so on. So that's what my group has been working on. I have also an example that's related to Job Corps data set. I'll just skip to maybe the final results, which basically says, think about individuals who haven't finished high school education and we give them opportunity to do so. Is that beneficial for their income, right? Will they gather bigger income later in life? And the answer is no. If your goal is just to give them a high school degree, instead, if you give them vocational training, then yes. So think about just getting a high school degree versus getting a mechanics training. Mechanics training earns you better income later in life. For this population, clearly. Does that make sense? But it's a little bit interesting because everybody would like to say, oh yes, higher education better. It's a more nuanced problem, right? And you have to think about it a little bit carefully. So I'll stop here. Thank you for enduring with me. I wanted to do a plug-in, I'm sorry, because we have a new journal, which is the first journal between statistician and Association for Computing Machinery. It's called Journal of Data Science. I am one of the editors. If you scroll over the QR code, it will get you to the website. Think about sending your papers there. We hope to be better than Neuralips, ICLR, and so on, and have some more maybe topics that are not typically covered, or maybe not only focus on positive results. Let's explore science as science should be done. So we have big ideas, but you can help us. We need you. So thank you.